I thought it might help if I unmuted. My apologies. Can you guys all see a PowerPoint with some termite mounds on it? Hello?
Yeah, yes.
Okay, good, good. All right.
Yes.
So I just wanted to verify. So what I wanted to show you really quickly, since it's a short time period, is some work that a student of mine did a little while ago on trying to coordinate the exterior shape of termite mounds and see how it correlated to climate, to soil types, and to the species of the termite. So here you have, let's see if I can remember how to do this. I can't remember how to do this. I have to learn how to annotate in Zoom, my apologies, but there's a cathedral mound, a large conical mound, a smaller conical mound, a dome mound, and what's called a mushroom mound. And what he did is compared basically the form of human structures. So if you look at the common ways that we develop human habitats, we look at materials, loads, and culture. And from a termite perspective, that would be what type of soil do they have? What's the climate? And what is the species of termite that's building it? And so he, it turns out that you can have the same species of termite make very different, or you can have different species of termite making the same form of termite mound in different climates, or different species making different termite mounds depending on climate. And what was interesting was after classifying, I think he looked at about 65 published works on termite mounds into cathedral, dome, cone, mushroom, and meridian. Meridian mounds are very specific mounds found only in Australia, and they are directional. They run north-south. Looked at environmental conditions. So he did a lot of GIS mining to find out what the standard climates were for these areas where the termite mounds were. Looked at the different soils that existed and that were listed in references on different termites. The purpose of all of this was to develop a sort of 30,000-foot look at mounds, because what happens is typically mounds, you need to be there to be able to study them. And so if you're, it's very difficult to look at a lot of different mounds and a lot of different species without a really high travel budget. So this was a meta-analysis of what was going on. And what he found is that soil, the soil that's prevalent in an area has a much higher influence on the shape or the topology of the outside of the mound than climate does. For meridian, cone, and cathedral mounds, the large mounds that you get, there's a lot more sand and a lot less clay available. Dome mounds, you have more clay. You don't have the sand, which gives you the ability to build larger and actually have some stability. So to a great extent, it's a materials problem. So he looked at clay and local soils for different mounds. So different size of conical mounds, the larger percentage of clay you had, the smaller your cone was going to get. You needed a smaller clay percentage and more sand to get the larger mounds. And again, I'm trying to do this all in 2 minutes. Climate seemed to be a less apparent correlation than soils. There really wasn't a high correlation there, which sort of goes against a lot of the conventional wisdom and publications on what termite mound shapes look like. So what we did was develop a database of termite mounds, which at the moment is not up, and I'm ready to kill an undergraduate student. But I did want to point out that I'm going to switch my screen in just a sec. So let's go back here and I'm going to stop share, and then I'm going to do if I can get back to where I was. So I'm going to do a different screen share here. And let's see, yeah, here we go. So this is the website that we developed. I think it's the 3rd generation of it, But so the termite mound topology project is looking at the topology and shapes of mounds, and right now we're funded to do it from a micro scale to a macro scale. So we have the previous NSF project that we did, the current NSF project that we're doing, the database, which if it doesn't get up soon, like I said, I'm going to find an undergraduate student and strangle him despite social distancing. The team of people who have been working on these projects, they run from civil and mechanical engineers to our in-house entomologist to my husband, the climate dude, to one of the best grad students I've ever had. And then there's a spot where you can actually send us information on a mound or ask us for more information on the project, which I also have to modify because it's about a 95% spam hit right now. And I've had 2 people actually email me with real questions, but that's where we're at for now. So I probably did more like 4 or 5 minutes, right? But that's one of the aspects that we're doing. We have a couple of different things that we're doing on termite mounds right now, but we really wanted to see what it was that caused the exterior shapes to differ so much across species and climates and continents. And a lot of it basically boils down to what soil they've got. So we have to do a multivariate at some point, but that's where we are for now. So was that lightning enough?
Yeah, it's very interesting, actually. So I'm gonna say for each of the lightning session, do you all want to ask questions, or you want to save it towards the very end? How about we just ask questions for each of the talks? That way, we don't forget what we're about to ask. Any questions from the audience?
Okay.
Actually, I have a quick question. I've read a little bit on how there are some buildings in infrastructure, or maybe around the world, that kind of mimic termite mounds for energy saving purposes. Are there any other applications that could be garnered from the study of termite mounds for built infrastructure?
That's going to be the biggest one is energy savings. But if you look at some of the work they've been doing at Harvard, there's a lot of stuff with termites for like autonomous construction. So can you just, they've got the Termes project, which was building small robots that would autonomously pick up little pieces and then construct something. So that's one of the other things. So the process by which the termites decide where to pick up a piece of dirt and where to deposit it has been very highly studied. We're also looking at the multi-porosity aspect of the mounds themselves. So we're going from looking at it almost like a concrete materials project, but looking at very, you know, at the porosity between the different elements to the smaller tunnels that show up, and then the large central tunnels that you see, and seeing what kind of patterns there are, predominantly for like ventilation aspects. So how is it impacting the homeostasis of the mound that they have these multiple levels of porosity? So.
Okay. Hey, Andrew, I think I'm going to ask myself something that I'm very interested in. I think you briefly touched that. There's a hierarchical porosity that exists in most of the termite mounds. And termite mounds are known for the self-ventilating features. Mm-hmm. I don't know if it's too early for you to answer in the project now, or have you guys figured out what is the primary mechanism to drive this autonomous, let's say, airflow for self-cooling effect in termite mounds?
No, and there's there's a lot of work being done on that. We're actually looking at the material itself more than the construction methods of the termite, other than we're trying to determine the actual process by which the dirt gets like constructed. So we're looking at mechanical versus chemical components in terms of the cementation, or probably better put, the adhesion of the soils. Again, I'm going to go back to Harvard because their physics group there has been doing some work on the ventilation. But one of the possibilities, one of the new theories, is that the ventilation is almost, it's more driven by humidity than airflow.
Oh,
So they're essentially marching towards water. I don't know, this giant termite mound that's the background for the website right now. You can see the darker spots are actually where there's been active build going on, and it's always about water. The last trip we had out there, we actually had to water the termite mounds. We had essentially IVs set up on the side because it was so dry down there. So we had these large bottles of water that we, for lack of a better word, saran wrapped to the termite mounds, and then had an IV flowing into them so they'd have enough water to build so we could get samples. But yeah, there seems to be a huge humidity flow, more so than necessarily airflow.
that's very interesting. I've known this for the first time actually. So looking forward to the outcome of this project, and it's a very good website. I love it. So
Cool. Yeah, I want the database back up. It's a great database, and it's just a matter of we ported this over to WordPress to make it more to make it easier to edit. And then we had a hard time getting the database over. So anyway, I'm going to stop sharing for now and pass it along to the next person.
sure, thank you very much. So the next talk will be the architectural implementation of a topological optimization on discrete structures by So Wu from Waterloo. So I'm going to turn the stage to you, and then so if you want to share your screen, it's on your bottom of the control panel.
Can everyone see the slide?
Yeah.
Okay. Hello, everyone. My name is Sue. I just finished my defense a few days ago, and this is a summary version of my thesis presentation at the University of Waterloo. And again, I'm here to present my work thanks to an invitation from Dr. Elizabeth, who is a professor at Waterloo. And my research is about using an engineering tool as an informative guide to create a novel architectural design. And my particular interest is on architectural implementation of topology optimization in discrete structures. For more efficient communication, I will be abbreviating the term topology optimization as TO. Personally, I was introduced to topology optimization by this project designed by Pritzker Prize laureate Arata Isozaki. And this project is a convention center located in Doha, Qatar. I think everyone knows about this project because it's very famous in biomimetic design. As you see in this picture, the most prominent feature of the design is a pair of massive tree-like structures that support the roof over the main facade. And I found these structural elements were the product of a type of topology optimization algorithm called evolutionary structural optimization. And use of this algorithm results in natural forms that are very much relevant to the field of biomimetic architecture. And through my research, I found these structural there are two major types of structures that utilizes topology optimization, and one is continuum and the other is discrete structures. And there are many realized projects in terms of continuum structures. The major research group that focuses on organic form finding using TO algorithm is the Digital Building Technology Lab at ETH Zurich. And these pictures show their recent projects called Smart Slab and Concrete Choreography. Both projects involve robotic 3D printing technology, and for the slab, it was the formwork that was 3D printed, and for concrete choreography, the columns themselves were 3D printed hollow with some fillings. When it comes to examples of discrete structure design, there is few ongoing research. MIT Digital Structure Lab is one of the active research groups looking into the application of TO to discrete structures. The algorithm is employed to create various structural solutions in the same assigned problem. After researching the applications of topology optimization on discrete structures, I realized that the majority of applications are limited to the design of funicular structures. And this begs the question, what happens if we want to apply topology optimization to non-funicular atypical type structures? For example, when structures are exposed so that they become a part of the aesthetic scheme, then the design of those structures are not primarily interested in structural performance. And I called these types of structures atypical structures. And the choice of atypical structure system is driven by architectural parameters, where designers' choices are heavily impacting the design. And these parameters are not general and vary by project. And for architectural design, sometimes it is based on the site, and sometimes it is based on culture and social dimension. And I believe designers can input their creative agencies by choosing appropriate structure systems when using topology optimization. In this design study, methodology for design implementation starts with two parameter inputs. One is architectural and the other is structural. And first, the structure system is determined by the designer's choice based on chosen architectural parameters. As a parallel process, topology optimization algorithm is executed in a Karamba 3D parametric script with the structural parameters such as domain, external load, and support setup. And finally, the design is created by combining these two outcomes. I would like to describe the major architectural parameter that was used for my design study. The site for my design proposal was Seoul, South Korea. And a quality that I wanted to incorporate in my structural system was this wooden frame that you can see in vernacular Korean architecture. It's called chang. And this frame comes with a simple grid geometry, although sometimes it is composed of complex ones. From inside, the landscape through these openings is framed by this decorative frame and creates a unique spatial experience that the frame itself becomes a part of the landscape. And I wanted to create a similar effect on my lattice element design. So the lattice element design was created by combining these Korean screen patterns. The idea was to replace a solid walled HSS column or beam with a patterned lattice structure. And for structural parameters, external loads and support conditions were set up to execute a topology optimization algorithm through a parametric script. Horizontal and vertical forces were input as the external loads, and the bottom had the fixed condition for the column design. And after that, a series of trials were performed to identify the range of forms that could be achieved, and the results were plotted in a matrix based on the proportion between vertical and horizontal forces. And on the right is one such result driven by TO form generation. And this will be carried through in the illustrative example here. And this is a combination process after executing the topology optimization on element form generation. The resultant TO forms were combined with the chosen structural system, which is the lattice discrete structure for this study. And since this pattern is not inherently structural, I introduced reinforcement to reduce the required loads, and it is some sort of sizing optimization. And to accomplish this, the topology optimization form is used as a guide to reinforce the material along critical load paths within member. And this illustration shows the final result. I tried different thickness multipliers for the reinforced members for the sake of visual comparison. The right image shows the final column design with triple reinforced TO guided lattice column members when the base thickness was 2 centimeters. And this is a conceptual drawing demonstrating spatial qualities of the overall assembly when these members are put together as a building. The layout of the overall assembly is also guided by topology optimization. However, for the sake of brevity, I omitted explanation of this process for this presentation. And this is an interior view showing the effect of structural framing. One of the aspects that I wanted to deliver architecturally was that the decorative framing becomes a part of the landscape, which you can experience a similar quality from vernacular Korean architecture. So this is the end of my presentation, and thank you very much for your attention.
Thank you. So, any questions for her? Very interesting.
Guillermo has a question, if I may.
Yes, please.
Thank you. Very interesting work, and I really like the final geometry that makes a beautiful architecture and make it very nice. Now, with regards to structures, the areas that you optimize, were they based on a type of failure, like buckling failure, bending failure, where you decided to then add reinforcement? Or what was the criteria that you used for the optimization? Was it a structural failure, structural mechanics, structural design, or which one?
Yes, for the column design, it was subjected to axial load, and then the horizontal load was the between the shear and the moment. So the moment was converted to the shear force, and then both were applied to the topology optimization script.
What about in high earthquake regions? Do you expect to have a much different result?
Sorry, I couldn't hear you.
What about in highly dynamic regions, earthquake regions? California, Puerto Rico, the Caribbean, that is highly dynamic events. They're having highly dynamic events. Are you considering those forces for this optimization?
This is a speculative form finding and architectural form finding, so they were simplified assumptions, and dynamic loading was not considered.
Thank you very much. Very good work. I enjoyed it.
Thank you. Wonderful. I think the next presentation would be mine. let me try to do the screen share right. This last time it went to the wrong screen. Okay, great. Can you guys see, can you see the screen okay? It's a slide? Okay, great. I think today I'm going to give a very brief synopsis about a few things that we have been doing in our research group with my students. I will not talk about them all, but rather probably the first two at a very high level summary. One is the application of a computational graphics approach called Brown tessellation and how they're being applied to design adaptive structures. And the second is I want to talk a little bit about a recent project we started not too long ago on using the venation generation technique in combination with materials to do evaporative cooling, particularly how we try to draw the water, gray water of building from ground level to wet the building envelope for energy saving purposes. So the Brown tessellation, I think I probably have talked about this in last year's session briefly, is basically a pattern that widely discussed in nature, a discovery in nature from the pattern of tree leaves to the skeleton of dragonfly, microstructure of turtle shell, and so forth. So ideally, the concept of Brown tessellation is very simple. Our objective of this particular research was how to take that pattern that people learn from nature and then apply it to the design of a building component, for example, for either structural or architectural purposes. So the concept of Brown tessellation is, again, very simple. That let's say if we have a given random set of points that people often call those generator points, if we draw the bisector lines in between of each of those points and the collection of these lines then forms what we call a Brown pattern. So the interest of the property of Brown pattern becomes more interesting if people try to match the gravity center of each of the cell. Those are the ray dots by integrating the density function across the area. So typically for random sets of dots, the Brown pattern generated, the generator point will not coincide with the center of gravity. So there have been a few computational approaches trying to basically design patterns that with those two dots coincide. Those are what people call a centroidal Brown tessellation. So centroidal Brown tessellation has a very interesting pattern because if people start with a very random set, no matter what this starting point look like, by applying this computational approach, and eventually, if these generator points and its gravity center coincide with each other, then this distribution of those points will match how the density function basically distributes. So this is kind of a very simple demonstration of that. If we have a non-uniform density function with a higher on this corner and lower going across, and then those points eventually will converge to these higher density points. So how we are using that feature to guide the design. This is one of the projects that my student did earlier as a demonstration. Say, if we want to design a lightweight structure, for example, we take a femur bone and apply different load condition on it and run finite analysis to get the stress. What he wanted to refine back then was to basically refine the microstructure around where the stress change is high. For example, like those stress concentration point. So what he basically did is to take the stress gradient function and apply that as the density function that drives the computation. And what happens is that we started with a very random set of points in the domain, and by applying centroidal Banach tessellation, and then those points basically will redistribute to concentrate into the areas of high stress change, for example. So that later on gets applied to design light wave structure by designing the cutoff pattern, for example. Again, we use the case of ephemeral bond just as illustration. Then this technique basically gets applied to design anything from a beam to a shear wall. But yeah, of course, the final pattern that's been designed, it's quite difficult to construct. Well, later on, we basically take that approach and did a few different things with it. One is the design of modular structure, and also a thermal adaptive building envelope, and the optimization of geothermal applications, for example. So as a very simple, I guess, synopsis of what we have done, we take this approach, then take the CBT from 2D to 3D. This was a work that was done in Italy that our group didn't do this particular method. We kind of borrowed it from a computer science paper published in 2015. So what we have done with that is we basically hypothetically designed what we call active cooling building envelope by passing water into those skeletons of, for example, building facade panel. Those skeletons are active cooling water lines, and same time serving as the structural frame for those facade panels. So we have run some preliminary analysis and see how we can design the pattern distribution, for example, for a glass dome, based on the hotspot that happens during the daily solar cycle during the day. So, and another thing that Jen Lai, who is also online here, has been trying is to look at the geothermal applications using the same approach, particularly to guide the design of a borehole field. And one of the challenges that our colleagues from geothermal technique has been encountered is once a geothermal or borehole field is being designed, and typically people use uniform grid to deploy the locations of those piles. And over time, what happens is that the center of this field will be cooled down. So the temperature difference between the ground and those thermal piles becomes fairly small, and a large portion of those thermal piles will become very ineffective. So we have been using the CVT technique and try to help the design to level out this temperature difference in a way that over the 20 years period from the initial construction, the thermal pile will maintain a relatively uniform temperature, and at the same time that give the maximum thermal output. So the second project that we have been sort of trying is to apply the concept of evaporative cooling, which is not very so new, but to look at in a way that for evaporative cooling, a lot of challenges that we have been seeing is the water supply sources. So when people are trying to use gray water from building to do the cooling of, for example, envelope, and people preferably want a system that doesn't have the complex plumbing system and as little as energy input as possible. So one of the things that we're looking at right now is to see how vascular plants, particularly tall trees, are drawing water from ground level to high locations of the top of the plants through the transpiration process. So particularly what we've been looking at is basically a combination of geometry plus material. So within the plants, from the leaves to stems, and there is those vascular structures and filled with a substance called xenon. So these are the nanoporous structures that are responsible for drawing the water through vascular effects. But when they achieve to the leaf level, the leaf does two things. One is use the venation pattern to distribute the water to a large uniform area. And the second is enable the evaporation process that creates a high negative pressure and drive the water from the ground level to higher up. So kind of centered around this idea that we have been doing two side of work. One is to create a artificial xenon, which is a nanoporous structure, a form of hydrogel inside those venations for water transportation. And the second is to design a material that has mimicked the structure of a tree leaf, for example. One is to enable the water to uniformly saturate the material and also speed up the process of evaporation for cooling process. So I will skip some of the technical details about how the venation patterns are generated and how the materials kind of work together. This is an ongoing project, and we're trying to get some preliminary result at this point. So that's the two things I think I really want to discuss today. And on top of that, well, we have also been working on dynamic building envelope that changes thermal property as a function of temperature or climate condition, as well as ways to use additive construction or manufacturing technique to achieve spatial patterns. So Andrea talked about termite mounds as something that we want to really look at in the future. Hopefully the projects that she's doing right now will basically inform what's going on next. One of the designs that we had from before was to design a building envelope pattern that's made of concrete, and how we design the internal porosity patterns to enable the self-cooling effect by drawing air from the bottom and flow autonomously to the top. So she was mentioning earlier that's probably the process more driven by moisture, which I'm very, very interested in to learn more about that. But the way that we basically created those patterns like this is we 3D printed what we call the internal mold, which is made of material that's meltable, either a form of water-soluble polymer or wax. And then we kind of pull concrete around it and then melt the coal out to form a rather complex shape and a relatively large scale. So that has been a few things that we are currently working on. And without taking too much time, I think that's all that I have. So is there any question or comments? If not, I'm gonna jump to.
A very interesting presentation, very nice. So my compliments. And also I would like to ask you, maybe I can get in touch with you later to get some indications about some bibliography, your papers, because you touched on many, many topics. So really interesting. Most of them I could understand something, but very quick, very fast presentation. So I would like to deepen some. So if you can give us some more details about papers or bibliography, this would be wonderful.
Yes, absolutely. So in the presentation, I think I have included a few sources of citation, especially if we have used other people's work to drive the, especially the computational side. So let me try to reshare the screen real quick. So for example, like the Brown tessellation work, especially taking the work from 2D to 3D, that we mostly refer the paper that was published at a computational conference in 2015. That we wrote our own code, but it's based on the series presented in this paper. So this was, to my opinion, a very big leap that's going from the 2D applications of the Brown tessellation to hyper surfaces, basically any random surfaces, and the projection method that's presented by this paper is very interesting. And the cooling project that we're currently working on, we are doing anything from basically the geometry to material, but there has been a paper published on Nature, I think, in fairly recently, I think in 2018, that discussed the fundamental mechanism of how the transpiration was able to transport water from ground level to a very high altitude for some plant species. So so I'm including some of those here, and also at the end of this, I will send everybody the link to this recording that we have now. That way, we will have the information of the slides, all the information on the slides.
Perfect, thanks.
Thank you. So we're gonna move to the last but not least, the present lightning talk by Austin Dada. And he will talk about bio-inspired materials and the interdisciplinary education of structural engineers, which I feel is a very exciting topic, because that's multidisciplinary is basically the soul of this committee. So with that, I will turn this to Austin.
Okay. Here. Okay. Thank you very much. Can you all see my presentation here?
Yes.
Yes.
Okay. Thank you.
Yes.
So my name is Austin Dada. I'm currently a PhD student at the University of Colorado, Denver, under Frederick Rutz. As I said before, I also work as a bridge engineer at Roxol Consulting Group in Denver, Colorado. And my major course of study at UCD is in Engineering and Applied Sciences program, where we're tasked with interdisciplinary study between an engineering field and another science or a math field. So I'm studying the interdisciplinary nature, I guess, of structural engineering and biology. So, which at first glance doesn't seem like a compatible area of study, but Tom Knight, a scientist at MIT, pointed out that biologists and engineers are very different, and the fact that engineers are more concerned with standardization and applicability in general, while biologists relish more complex topics. So my immediate goal in my studies here, I just started last fall, is to determine a curriculum of study that would effectively give an engineer the tools that are necessary to study and apply biological concepts in the field of structural engineering and construction. From my preliminary literature review, I've come up with the following emerging applications in the field of bio-inspired structures, which you can see in this slide here. For the creation of new biomaterials or the use of existing biological materials in construction, I've studied the familiar concept of hierarchical structuring in the strongest natural structures. In the first photo, you can see the comparison between the similar hierarchical structure of bone on the top and bamboo on the bottom, followed by another photo of the hierarchical structure of silk. The concept of the occurrence of hierarchical structuring in nature would be crucial to any potential curriculum regarding bio-inspired structures. Another application deals with determining properties of conventional construction materials. One example of this application would be the use of structural color, which is employed in butterfly wings and can be used to identify changes in strain and corresponding stress in construction materials due to their change in color. So these photos from left to right show the application of a film. Excuse me here. That creates an anti-reflective layer on a nickel coupon and concrete treated with a bacterium which excretes calcium carbonate, effectively sealing microcracks. So the concept of inducing an anti-reflective surface or healing, self-healing properties in a material would also make for a suitable study topic in the creation of bio-inspired structures. Hierarchical structuring can also occur at the macro scale, as many of you know, as seen in these two photos, where the bending moment distribution of a tree branch is shown, as well as the structural system of a frame on the right, also known as a diagrid, where a structural system similar to that of a tree trunk is employed for increased structural integrity. So I went through a lot of literature and determined that several basic biology courses can be taken in order to achieve a better grasp on the concept of biomimicry. As shown in this slide, you can see advanced and microbial ecology, just a course that would detail how different biological systems work together, biochemistry, cell biology, molecular biology, and microbiology. But as shown here in this slide, some institutions have already created more applicable coursework, which gets to the heart of the concept. So along with Northwestern University, other institutions have similar coursework, including a biomimicry course at Georgia Tech. So the key to all of this is to create a curriculum and a field of study that doesn't simply employ superficial mimicry of biological structures, but also employs the full breadth of energy efficiency and advanced structural integrity that biological structures have cultivated over millions of years. My final goal regarding my PhD studies is to determine a research topic. So hopefully I can use the expertise of you all in this committee in some way to receive some help in moving towards that goal. And I'd also like to thank Dr. Mahmoud at Colorado State University. He couldn't make it to this meeting, I believe, but he was really instrumental in helping me find this group, along with Dr. Rutz. And he also, Dr. Mahmoud told me a lot of things about structural systems and how those can mimic biological systems as well as resilience. And I'd also like to thank all of you today for listening to my presentation. Thank you.
Thank you, Austin. Great talk. Hassan cannot be here with us today, but he's a very active member in this committee as well, and he has been involved since the very beginning. Any questions for Austin?
I just have one suggestion. Austin, in your last slide where you show the different classes or the different topics that need to be covered, there's one main topic that is missing, which is materials. What are the materials properties of the biosystems in comparison to the material properties of the common materials that we use to build our structures? Materials is essential in this topic.
Okay, yeah, absolutely. Thank you very much.
Austin,
Right.
oh,
Go
sorry.
ahead, Andrew.
Well, I was just going to say, I'd like to get you in touch with my current PhD student because she's charting new territory as well in terms of her PhD study. She comes from a MET background, so she's all about materials actually. And she's been working on her plan of study for the PhD in our MES program, which is Material Engineering and Sciences, or it's an umbrella program that covers a couple different departments. But she'd probably be happy to talk to you about the kinds of courses she's taking. And again, she's coming at it from more the material side than the structure side. The other thing is, I'm not sure what exactly is it about biomimicry that completely fascinates you, but from a structures perspective, the project I will never get to is social weaver nests. Have you ever seen them?
Social.
Yeah, social weavers. If you look up social weavers, they create nests that are essentially like bird condominiums. And they can weigh like a ton in a tree. And they, like most bird nests, are made from predominantly brittle materials. So how do you get a 1-ton, essentially tensile structure to hang from a tree to hold an entire community of birds using tensile structures or using, using brittle structures? So I just think they're fascinating, and I know I'm never going to get to it. I'd love to. It's just not going to happen. So it's all yours.
Thank you very much for that. I'll definitely be looking into that. And should I contact you after this for the contact information of your graduate student?
Yeah, drop me an email. That's probably the easiest. I actually have a Zoom meeting after this because life in these ages. But yeah,
Right.
yeah, I'll look you up with Hannah because she can probably give you some insight on what hers looks like.
That is perfect. Thank you so much.
Sure.
Yes, that's something that I was going to say, that the whole purpose of the lightning talk in this session is to facilitate collaborations. That I think this is great. And Andrea, can you also send the bird nest name in the chat station so that?
Oh yeah. So actually, if you're done, I can share. Let me share a screen really fast. I'll show you what these bad boys look like. I can. Let me get a good image up. Unfortunately.
Hey, while she does that, Austin, this is Mark Wagner. That was great. I enjoyed the presentation there, and look forward to what you come up with.
Thank you.
One suggestion as you consider all of this, don't forget about sort of the construction process. I think a lot of times some of these biomimicry efforts end up with a object that kind of imitates something, but you sort of consider unbuildable with kind of modern technology, the construction technology as it is. I think there are some analogies in the way that things grow that mimic construction. I would just encourage you to incorporate that as part of your thinking process and not just think of the end product alone.
Absolutely. I'll definitely keep that in mind. And I really appreciate that suggestion as well. Being a practicing engineer, I'm definitely kind of just, my brain is already geared towards construction, being on construction sites all the time and things like that. So I definitely appreciate that contribution as well. I'll be keeping that in mind as well.
I have a couple comments. It's a couple dissertations that came out not too couple of years ago. One is Dr. Wayne Hodo, Hodo. It's a very interesting by inspiring materials dissertation, and I think he was in North Carolina State University. And the other one is from Reena Patel, Patel, Reena Reena, from Mississippi State University. I will suggest you to take a look at those two. Very good reference.
Thank you very much.
So if I'm sharing this, these are what social weaver nests look like. They're
Very interesting.
you see them a lot on like telephone poles, and I've seen a couple of them. But the interesting thing, or the thing that I find fascinating, other than the absolute scale of them, because I've seen, oh God, I have a picture of one in Namibia that was huge, but you know, we're still talking about woven straw here. So it's a giant tensile structure made from brittle materials. And that's why I think they're interesting. But again, I'm just going to throw that idea out there because I have a feeling my career is about to take a complete left turn in the near term. So the other thing I'll throw out there is I'm presuming you've looked at Arizona State's master's program in biomimicry.
Yes, I've actually heard about it, and I've come across it in a lot of my reviews and things and readings, and I haven't looked into it specifically yet, but I've come across it, definitely.
Well, it actually strikes me that it would be a really interesting proposition of this particular committee to develop an undergraduate program in biomimicry with a civil engineering perspective.
I think that definitely can be discussed because we have a good academic representation in this committee with the help of practitioners. I think that's possible.
Yeah. All right, I'm going to stop sharing for now.
Okay, great. I think this first lightning talk session is really what everything that I have imagined, and it's going really great. And like I said, I really look forward to continue this tradition in our future conference meetings, the committee meetings. That way, well, another reason that we kind of did this, I think Andrea and I discussed in previous years about when we propose session to Structural Congress, it's hard to get them accepted. And people typically put in a lot of efforts. I think this at least provides a revenue annual for people to see what we have been working on. And some of our committee meeting actually take place in Structural Congress, have good attendance. So I think we're going to try to continue this tradition from now on and see how that goes. So I'm going to do the screen share again. And before I do that, I will stop the recording. See if I can get this right. Oops, let me do this.